Hello, good morning, everyone. Welcome again to our second session of talks. Challenge Talks is the name. And we are going to have four very interesting presentations. Stephen, do you want to put your first slide? What I see is a setup. Okay, excellent. So our first presenter is Stephen Powley from Coventry University, and he will be entertaining us talking about multi-context modeling for MDE, and the floor is yours.
Thank you very much, and thank you to MDENet for the kind invitation to join you today. So I'm going to pick up on a theme that was discussed yesterday morning as well. Yesterday we were talking about multi-level modeling. I'm going to present a slightly different take on multi-level modeling, and then a broader take on multi-context modeling and how that might be useful for MDE. So my background is as an embedded software engineer, and in the last decade I've moved into systems engineering, and I'm currently writing up my PhD thesis. And what you'll see today are ideas that will be in my PhD thesis and have come out of my investigations into the application of model-based systems engineering and ontology engineering to the field of automotive cybersecurity. But I'm not going to be talking about cybersecurity today. So I will first of all set the scene. Then I'm going to talk about multiple systems of interest. Then I'm going to move to a broader look at multiple contexts. And then I'm going to present the MDENet challenge, which I've been asked to bring into this challenge talk. And then we'll have a bit of a summary. So the problem is that models generally only capture systems at a single level of abstraction, and they do that in a single context. So that context might be, for example, the business that you're working in or the research project that you're working on. And typically an engineering business, my examples are going to be from automotive, but we'll have lots of different models serving lots of different purposes. And the goal of digital transformation, which is what I'm focused on, I'm looking at building enterprise capability, is to build the connections and bring and build linkages between those models. And we're working towards a model-driven enterprise, as it was described yesterday. I like that term. So there are advantages of separate models, as Dijkstra told us to do. We can easily separate the concerns, and we have good granularity on the configuration management, and it's much easier to control the model. But there are disadvantages to doing this as well. And if my slides will, there we go. So this established practice has its disadvantages, and in particular, in model-based systems engineering, model-driven architecture, systems engineering in general, we're interested in viewpoints that address multiple stakeholder concerns, and it's particularly difficult when you've got multiple models to address non-functional concerns that span multiple points of view, such as security and safety. It's harder to develop functions that take advantage of desirable emergent properties. It's harder, in particular, to share model parts effectively. So if you've got no control over the way that other parts of the business or your suppliers are doing their models, it's very difficult to share model parts, and that takes us back to some very crude document-based interfaces very often, and that's really a big goal currently in systems engineering is sharing model parts through the supply chain. And multiple representations of the same system element end up with conflicting terminology and definitions. And from an MDE perspective, that makes it difficult to generate the transformations. So the first part of the talk is going to be about representing multiple systems of interest in a single model. So this was originally presented with my industry supervisor for my PhD, Simon Perry, and there's a link there if you want to read the paper. So let's have a look at that. So this idea of different perspectives in a hierarchy goes back a long way, and there's a nice quote from Koestler from his book Ghost in the Machine, which, if you're interested, did actually inspire the name of the Sting song by the same name. But yeah, this idea is that depending on where that you look at things, or where things are being looked at from, that they can take different shapes, different forms in the eye of the beholder, which Koestler called the Janus effect, after the god with two faces looking in different directions. And here we're looking at subholes in a hierarchy. And this is something we do very, very commonly in systems engineering. We break systems down into smaller and smaller parts. And that gives us a hierarchical set of these holons. But the thing with a holon is it has characteristics commonly attributed to wholes and to parts. And we end up with multiple systems of interest at different levels of granularity. So I'm going to show you an example in a little bit where we have a printing machine, and for the organization that's building the printing machine, the machine is the system. But for the organization that delivers the flywheel that keeps the printing machine running smoothly, the flywheel is the system. So how can we deal with that all in a single model, but maintain those perspectives that are important to the various stakeholders through the supply chain? So what we do is consider a very simple model of a generic system structure. This is excessively simplified. I know there are some slight problems with the multiplicities on this model, but bear with me, and I think you'll find it serves the purpose for today. So each system is made up of system elements, and for today's purposes we're going to consider that a system element is itself a type of system, and that's very important to how this works. And each of those systems, and by extension systems elements, is interpreted in a context. So that led us to the development of a very simple SysML profile. If you leave off the block in the left-hand corner, it becomes a UML profile. I'm going to assume that everybody understands the SysML UML, but just quickly, the solid line here is an extension of the meta class, and the unfilled arrowhead is a generalization. So the system element extends the system meta class, which extends system class, which extends the class meta class. And then we, in this example, we have context as a package. And the trick here, which you can do very easily in UML, is to have these two tagged values that relate the element to the context. This is actually a language independent technique, but we're using UML SysML to illustrate it. Now, you generally wouldn't have in a real business that idea of system elements. You'd probably call them subsystems, assemblies, components, as you see on this diagram. That's not a problem. This technique works just the same. You can build a profile in exactly the same way as I've shown on this slide. And what this leads to is this type of model when you implement a model using the profile. And the key to this is using multiple stereotypes. So at the top, you see you've got a single stereotype for the printing press, which is a system. But then when we go to the power unit, the thing that's providing power to the press, in the context of system, it is in the context of the Press Power Systems company, it is the system. It is not a subsystem, but in the context of the top level manufacturer, it is a subsystem, and that goes through. You can see here that if we look at the energy storage, then we've got that being a subsystem of the power system, but an assembly in the terminology of the press manufacturer. And as we go down the hierarchy, you can see we end up with 3 different stereotypes, because there's 3 different organizations involved in that in making use or manufacturing that subassembly. So in summary, one person's system is another's subsystem. Modeling tools don't support the concept well out of the box. We can get around that by modeling holons to capture concerns in context, and we can use multiple stereotypes in UML, SysML, in combination with tagged values to reference the context. And then that means that without a great deal of upheaval, we can adopt this idea within an existing MDE activity. So putting all this into a single model will more accurately capture those different stakeholder views and at different levels of abstraction. It's a simple approach based on proven concepts and techniques. You can add this onto existing models, which makes it quite a more attractive proposition. You can enhance the collaboration between the roles because people are able to deal with things in their own terms. And it increases the model richness, which leads to better engineering practice. And by having everything in a single source of truth, you can start to question the model and get better business intelligence. So moving on to multiple contexts in a more general sense, what we find is different communities use different terms to mean the same thing, the same term to mean different things. And even when they're talking about the same thing, they may use different paradigms to define the same concept. And that may, they've got different underlying ontological commitments, to use the theoretical language. MDE seeks to connect different worlds or worldviews. So ideally, our models should be able to accommodate all of the above. And if we do that, then that helps those digital transformation initiatives that I was talking about by giving us the ability to connect different tools and tool sets without having to force people to change the way they work. And that's very important for this theme that we're discussing today of getting these ideas adopted and used in industry. So here's a quick little ontology that explains how I've approached addressing this idea of multiple contexts. The basic idea at the top here is a description. Terms may or may not be made up of descriptions. Some terms are descriptive, other terms are not. My name, Stephen, is not descriptive of me, but then you might think of, President of the United States, that is a descriptive term, for example. We have definitions, and this is actually a type of description, but it's actually a role. And if you're familiar with using roles in modeling, this is a role here. But if your modeling doesn't support the concept of roles in its underlying ontology, then you can treat it as a generalization. So we have this idea of a defined term, which must be made up of a definition and a term. And what we have between defined terms is a set of relationships that can exist between defined terms. And I've used the simple knowledge organization system as the basis for my set of relationships between terms. I'll come back to that in a minute. But when we implement this as a profile, it looks like this. So we have the term and the defined term. And then you see this idea again of using tagged values to link the defined terms to the definitions. And we have context. Before I did an example with a package, you can also use a class as a context. And I've called it a context space here for the reason that it's being used very much like a namespace. There's good reasons in UML to do it using a classifier rather than a package because, for example, it allows you to have properties and it allows you to create relationships between the different contexts as well. So using SCOSS, SCOSS has this breakdown structure here. The ones we're interested in for a very simplistic look at this are related, close match, exact match, broad match, and narrow match. So if you think of the first example I gave you where we were looking at the machines, we would have been talking about exact matches. We were talking about exactly the same thing. Our model was treating exactly the same thing, but it was treating different contexts. But when we come to work in an industry context, in my case, I'm very interested in standards, and we find that standards define things differently. So we very rarely see an exact match for the same terminology. Turning that SCOSS into a UML profile, it looks something like this. And we've extended that in collaboration with the Nkosi Automotive Working Group to build some, to add some different terms. And this is only a few of the extensions that we've added. But a very important one is overlap. That's not covered by SCOSS, and that is really important if you're doing this. You'll find that you'll quite often get terms that in one sense are broader in one direction, but in another sense are broader in the opposite direction. So if you're doing this, I'd strongly encourage you to consider overlapping definitions. So then what you do is create a very simple diagram with your context space. You have a general vocabulary and you have a generic descriptions. And then you end up with a structure like this. And when you create your defined terms, that they exist within the context space where they're defined. What I've done is built an Excel tool. So talking about getting this adopted, getting people to use it, I've built an Excel tool that constructs the mappings. And actually, we ended up with a lot of different mappings, and we wanted to give people the opportunity to say whether they were closely matched or loosely matched as well. So people just select from drop downs in the Excel, and it constructs the definitions automatically based on some prompted drop down lists, which makes it a lot easier for people to interact. And then we just import that into the UML tool using the profile. And then you end up with diagrams like this. This is a very simplistic example. So on the left, we have the systems engineering standard in the context of 15288. And in the right, we have the automotive functional safety standard. And you'll see here that they have very similar terminology, system element and element, system and system. But in the narrower focus of the functional safety standard, we find that unsurprisingly, the definitions are much narrower. And what this tells us is that people in the same business talking about approximately the same thing may be talking about something very different. So this would be a red flag here, for example, that system is narrower than system. And that would then hopefully lead to conversations within the business and within the processes and the way that you interact between the systems engineering team and the safety team, for example. So this has lots of benefits. It helps you model many worlds or many worldviews effectively. You've got separation of concerns, but connections across the boundaries. It's a simple approach, again, built on proven techniques and concepts. Context means many things. It can be language. You could even use this for multiple languages if you were working in a multilingual environment. It could be across industry. It could be across time, even across locations, different teams within the same business. I see this as a prelude to developing transformations. It gives you a picture of where the transformations might fit best into a business, where you might be wasting your time trying to build a transformation. But whether or not you're interested in transformations, it's giving you that greater model richness again that improves engineering practice and gives you better business intelligence. So my challenge here is that we've got an MDE glossary, part of MDENet, which is a very good glossary. It's a valuable document, but could we capture the provenance of the terms and recognize the fact that those terms are used differently in different places by different communities? Could we develop an ontology that expresses the glossary with more clarity? Could we map usage across model-driven and model-based domains? And could we drive the whole thing with a model? I think the answer to all of those is yes. I've demonstrated some techniques by which you might choose to do that. And I would leave with the thought that the pursuit of universal meaning may be futile. And instead, you are better off trying to capture usages and their contexts. Thank you very much.